So, we discussed many things about light emitting diodes, and we saw that the direct band gap materials are typically used for preparing these LEDs, and then when a current is passed through this by connecting proper voltage sources, then the photons are emitted, light is emitted, and the wavelength which is emitted depends on the band gap, and typically the voltage that you have to provide for this LED to glow also will depend on that band gap and the wavelengths. So, lower the wavelengths, higher the photon energies, higher is the band gap, and more forward voltage you will have to apply to turn it on, and the vice versa. So, let us glow two LEDs and see how it works. So, this is how a single LED looks like. You must have worked with LED torch and LED bulbs. So, they contain several such LEDs in combination, but a single LED just looks like this. You have a transparent cover, so that whatever light is emitted by the diode, that can come out, and then you have these connecting wires. The sizes, as you can see, the sizes of these two are different. Okay. One is shorter, one is longer. This is to tell that this longer one is to be connected at the higher voltage side, and this to the lower voltage side for forward biasing. So, this is the P side and this is the N side. So, let us connect this, supply some voltage and see what happens. So, I have this 9 volt battery, but I cannot give this 9 volt on the LED, it will just blow. I will talk about that little bit. So, what I am doing is I have taken this wire, this is a heater coil, and I will connect this battery at the ends of these two wires. So, the one I am connecting and one I will connect when needed. So, this will go here. Okay. So, this whole 9 volt is dropped on this, and then I can take part of it, smaller voltages I can take from here. So, let me take the LED, and the longer leg I am connecting to this red connecting wire, and the shorter leg I am connecting to this black connecting wire. So, this is our LED, and then this longer one P side, that is connected to this end which is at higher voltage. In battery also this red one is at the positive terminal of the battery. So, this is a higher voltage point. Now, I will connect this to give this 9 volt over this, and then give the voltage to this cell. So, I am connecting close to this end, so that very small voltage is given to the LED, and you can see that the LED is not glowing. Okay. So, I connect it here, and you see that it is not glowing, because only a small voltage is given. Now, I am increasing the voltage. By taking it away from this end point, I am increasing the voltage. So, it is not glowing, it is not glowing, it is not glowing, and here it is. Here you can see, and you can also see that it is red LED. Okay. I will not increase the voltage too much, otherwise my LED will go bad. So, up to here nothing happens, and after this you can see that it starts glowing. So, this much voltage is needed to put it on. I have another one, and here also you have two connecting leads, one is longer, one is shorter. So, the longer one I am connecting to the positive side of the battery, and the other one I will connect to this other side, like this. Okay. So, this is it, and now I am giving voltage, and you see where it starts glowing. Very low voltage, this length is very small. I am increasing the voltage because this length is increasing. So far nothing happened, nothing happened. I am giving this much of voltage here and this much I have given, and now you can see. Now you can see it is glowing and you can see it is a blue LED. Alright. So, to glow this blue LED, I have to use a much larger length of this heater coil. See, up now it has started little bit glowing, and here it is. Here it is. Okay. And if I do it reverse, it will not glow, it is a diode. So typically these LEDs, the forward turn on voltage is, depending on the color, it could be somewhere say 1.6 volt for the longer wavelength, and maybe some 3.5 volts for the shorter wavelengths. So this will correspond to, or this range will correspond to blue, and this range will correspond to red. And you should not give too much of voltages after this forward turn on, because you know the diode characteristics. The diode characteristics is, in forward bias it goes like this. Suddenly it increases. Okay. So if this is, let us say, 1.6 volt, and the other, let me draw it another characteristic. Suppose one is this, and this is somewhere, let us say, 3 volts or 3.2 volts. This is I and this is V. This is forward biased. You can very easily make out that this curve is, this IV characteristic curve is for red and this is for blue. Okay. But then if you try to increase this voltage on this LED, then the current will suddenly shoot up, and that is not good for the LED. So one has to keep this in mind. Typically, the current which can go through these LEDs without damaging is around, let us say, 20 milliamperes or so. So when you are connecting LED in a circuit, take care of this. Suppose you have a 6 volt battery. And then you want to connect this LED here, right? You want to connect this LED here in forward bias, all right? And then this is 6 volt. Okay. So if you want to send only 20 milliamperes here, what you should do? You should apply some kind of a resistance here. And how much should that resistance be? Suppose this is red LED, then the voltage drop here will be 1.6 volt or so. Okay. So the rest is coming here. And how much is this? How much is this potential difference? This potential difference is 6 minus 1.6, and that is 0.4 here and 4.4, this many volts. And if you want I to be 20 milliamperes, okay, 0.02 amperes, then what should be the resistance? Resistance should be V by I, and that is 4.4 divided by 0.02 ohm. Okay. So how much is that? 440 by 220 ohms. So you should put a 220 ohm resistance here, so that it's safe, it is running safe. Whereas if you have this blue LED here, forward turning volt is 3.2 volts, then on this resistance you have 6 volt minus 3.2, and correspondingly you can calculate. And what if two LEDs are to be connected in parallel. Suppose you have a 6 volt source and then you want to connect one LED here and also want to connect one LED here. Now, to protect, if this is both of them are red, to protect separately you will need that 220 ohm here and 220 ohm here. So that this circuit ensures that the 20 milliampere goes here, this circuit ensures that 20 milliampere goes here. So, these things one should take care. In reverse bias also, typically that breakdown voltage for LEDs are not large, around say 5 volts or so. So, in reverse bias you should not apply more than 5 volts, otherwise it can be damaged. So, if you are in reverse bias, you have to take care that your voltage does not exceed this, and even if there is no current, there is very small current, even then if you reach this point, then large current can happen. Okay, so these things are to be taken care of. Now, let me go to another kind of specialized application of PN junction, and that is solar cell. Another kind of diode which is very popular. Everyone knows solar panels, everyone sees solar panels here and there. Stations are being powered by solar panels, and everywhere you are seeing that solar panels are coming in a big way. So, what it is? The basic unit is again a PN junction, a silicon PN junction. So, in solar cell, like photodiodes we talked, light falls on the cell, on this PN junction, and that light creates electron hole pairs. So, essentially that same mechanism, but then constructions are slightly different. You take some P type first, and then you diffuse on that N type and make a depletion layer, so that you have this PN junction, and this is transparent. So, you put some transparent things, so light falls on this, and depending on the wavelength, depending on the absorption properties, these photons may get absorbed here, may come to depletion layer, or may come here. What we are interested in, that photons should get absorbed in the depletion layer, or say one diffusion length on either side. So, the photons are falling here, and they are creating new EH pairs. Now, there is a catch here. This is silicon I am talking, and silicon is a indirect band gap material, and therefore, this radiative type of absorption is less likely, but still whatever is the probability of that is being used to make these silicon solar cells. So, let us draw our typical diagram that we had been drawing for PN junction, P side, N side, and depletion layer. So, you have the internal voltage, potential barrier, and all those things, and let us say we just keep it here open, nothing added to it. So, the voltage is 0, the current is 0, everything is fine. You have potential difference, potential barrier here, but then you have metallic contacts, and at the contacts also you have contact potential. So, finally, V is 0, I is 0, everything is there. But now, if I shine light and these EH pairs are created and the electric field is there in the depletion layer, so the drift current will be there. the electric field will drive the electrons to n side and these holes to p side, and therefore you will have accumulation of that negative charges here. They cannot go, the current is there, so you will have accumulation of positive charges here, you have accumulation of negative charges here. So the potential will be developed, a potential will be developed, and because of that potential you have some kind of forward biasing, which will at certain concentrations which will balance this reverse drift current which is going because of this electric field, and things will be settled. So in this case you will have some potential difference here, some potential difference here. I will be 0, there is no current, but there is a voltage difference on this p side and n side. So if I try to show it in an IV characteristic curve, suppose this is I and this is V. So where are we? We have some potential here, but there is no current, so current is 0 and we are here at a certain illumination. If you increase the illumination, more charge carriers will flow and the potential will little bit decrease, little bit increased. So at here this point is known as, or this voltage is known as open circuit voltage. If you take a solar panel and see the specifications, you may find this open circuit voltage. So it is there. What if I connect it to a load? First connect it by a almost resistance-less wire. So I just connect it. Then what will happen? Light is falling, and therefore EH pairs are being created, and therefore the electrons are going this side and these holes are going this side. So you will have a current here, you will have a current here, you will have a current here like this, and the current is in the negative direction. Okay, this p side, this is n side. Normally p to n we take as the positive current. When we do a forward biasing, any p-n junction, when we do a forward biasing, then the current goes like this. So this is our typical positive direction of the current, and here it is going in negative direction. What is the drop, potential drop here? The potential drop is 0 because no resistance. Okay. So on this characteristic, if I look at it, this point will be somewhere here. I have a current and the potential difference is 0. Since we have short circuited, this current is known as short circuit current. So this is short circuit current. And it depends on the intensity of this light which is falling here, and the absorption properties, which wavelengths are there and which are absorbed, and how many EH pairs are created. All those things will decide how much is the short circuit current for this particular conditions. Okay. Now in between, if I am adding a resistance here, suppose I add a resistance here, I connect some motor or something, some bulb, something, some resistance, load resistance is added. The current will be there, and if you have this RL here, some current is I, then I times RL will be the potential difference. And since the current is going this way, you will have a larger potential here, smaller potential here. So you have a potential difference on this p-n junction, as if you have given a forward biasing. This is the higher potential side and this is the lower potential side. So as if you are giving some kind of a forward potential. So because of that the current will be changed. If you do not have any light, what happens? If you do not have any light and you apply a voltage in a p-n junction, normal p-n junction, this kind, that characteristic is like this. You know that? That characteristics is like this for a typical diode. Now, if I am putting this RL and this side is becoming at higher potential and this side is becoming at lower potential, then I am doing some kind of forward biasing, and this kind of current will be superimposed on that photocurrent. Because of this light, because of this EH pair productions here, and because of this internal field which is drifting electrons this side and drifting holes this side, you have a current which you can call photocurrent. Because of the photons you have current. That is this current here, that is this current here. But then because of this RL, because of this voltage appearing here, you have a forward bias thing. So, this will be superimposed on this. If it is not there, then you have this current, but then on this you superimpose this, and your potential, this current will vary something like this, something of this sort. Okay. So, here you have that open circuit voltage, here you have that short circuit current, and in between you have almost very slow variation, and then it turns, and then it goes and it hits here. So, that is the kind of IV characteristic is displayed by this solar cells. What about power? Because we are interested in power. From solar panels, what we need is power. So, we have light falling in it, sunlight, normally sunlight falling in it, and then we put some load here, and so that we get some potential difference, we get some current, and so there is power. So, in this case when V is 0 and I is equal to I short circuit, power is 0, V into I is 0. In this case, when V is equal to open circuit voltage and current is 0, in that case also power is 0. So, power will maximize somewhere else, and normally it maximizes somewhere near this bend. So, this is it for this current and this voltage, right. When your system is such that you are at this point, current is this much, voltage is this much, then you have maximum power. So, this is current for maximum power and this is voltage for maximum power. So, these kind of considerations are there, and one silicon cell will give you open circuit voltage of about 0.5 volts. Okay. And then the short circuit current will of course depend on how much light is falling on it, but typically it will be in milliamperes. So, a number of solar cells are connected in series to increase the voltage. We may need a solar system for 12 volt DC or 6 volt DC or so. So, if you have 0.5 volt on one, you can put in series to increase the voltages, and then the current capacity also has to be increased. So, such lines can be connected in parallel, and then your current capacity can increase because of that. So, that is what you typically see in a solar panel. So, I have a solar panel for you. This is a solar panel. A panel means a combination of all those solar cells in series and parallel and all those things. And on the other side we have these two wires coming out, and I can show you the specifications also. See, the maximum power is this much, 3.0 watt, then the maximum power voltage and so on and so forth. So, maximum power current is 0.34 ampere, short circuit current is 0.38 ampere, open circuit voltage is 10.0 volts. So, this is the kind of specifications you can find on the solar panel, right. So, let us take this solar panel in sunlight. and drive some appliance, some motor or something with this solar panel. Let us do that. So, I have this panel here, solar panel, sunlight is falling on it, you can see the shadow, and then the two wires which are coming from the panel, they are here in this clip, and here is a toy motor, and we have put this fans here, so that one can easily see if the motor is running, and then the two ends of the motor are here, which I am now going to connect to the panel. This I am connecting, one side is connected and the other side is here. See what is happening? See what is happening? The motor is running at a very high speed, and if I block this sunlight, suppose I block this sunlight, see what has happened. Now, the sunlight is not falling on the panel and the fan is stopped, and now I am tilting it, so that yes, sunlight has started falling on it and you can see the fan. Stops, runs. Okay. See, if I make a shade with my hand, the speed is lowered. It is running, but the speed is lowered. So, much less number of hole electron pairs are being produced, much less electron hole pairs are being produced, and now many more electron holes pairs are produced. So, that is how a solar panel works. So, that is all about PN junctions. We had discussed the theory, the operations, and then the applications, varieties of PN junction diodes for special applications. And now we will start another section, and which is transistors, where you have on the same chip two PN junctions, and just putting two PN junctions on the same chip, you can create lots of applications, and we will talk about it from the next lecture.